Welcome back to Calculus 2, Section 7.2, Calculus of Parametric Curves. We'll start by looking at a derivative of parametric equations. Motivation. Remember that the derivative can be interpreted as the slope of the tangent line. Here we have a red line segment, nice and straight. We watched a blue dot traverse that line segment, given by parametric equations, x equals 6t, y equals 4t plus 2. If we go ahead and take the first equation, solve for t, plug that into the second equation, we recover a regular rectangular equation of this line. Y equals mx plus b. The m is the slope of the line, here 2/3. Note that that means dy dx is 2/3, 2/3. But also notice that 2/3 is the same thing as 4/6, which can be written down as y prime over x prime. In fact, we can take that as a theorem. That if you have a parametric curve C given by x equals x of t, y equals y of t, make the assumption that x prime is not 0, then the slope of the line tangent can be found in the quotient of y prime over x prime. This is the same thing as dy dt, quotient dx dt. Proof is dependent on the chain rule. We suppose that we have a rectangular form of the curve y equals f of x, but f of x can be written down as a function evaluated at x of t, which gives you a function y of t. Thus, y prime becomes the product of df dx and dx dt. Assuming that x prime is not 0, we're able to divide through and finish the proof. Okay. So we have a formula on how to compute the derivative. Let's do an example. Parametric curve given by these parametric equations. Let's suppose that we want to pick point P on this parametric curve, where P is given by parameter t set to 1. We know that we can find the coordinates of point P simply by plugging in t equaling 1. 2 times 1 is 2, and 4 plus 1 is 5. Next, we can look at, well, we want to use point slope form. What is the slope? We have a point, let's find the slope. Using the formula, we'll need a computation, x prime. We'll need y prime. And then we take the quotient, y prime on top, x prime on the bottom. Simplify, we get 4/3t. Then we evaluate that function at t equal 1. 4/3, that's our m value. Point slope form of the line, y minus y naught, take y naught to be 5, equals m times binomial x minus x naught. X naught is 2, and m, we just computed, is 4/3. This gives the line which is tangent to the curve at P. Excellent. Here's an assignment for you. If we have a parametric curve given by this same parametric equations, determine the equation of the line tangent at C at the point P corresponding to any t naught. We use t naught being 1. Explain why no tangent line is defined for t naught being 0. And then you can use Desmos to sketch out the curve C. And then think about this second part, why there is no tangent line defined, how it geometrically corresponds. Here in number 2, you want to algebraically give an explanation. Doing number 3, you can geometrically give an explanation. All right, so 7.2, we looked at derivatives. Next, let's look at a derivative of a derivative, second order derivatives. 2 things to note. One is that we have For parametric equations, the first derivative is the quotient y prime over x prime. And here I've just notationally adjusted that statement. From Calculus 1, a second derivative of a function y in x is a derivative of the first derivative. Okay. Using this notation here, if we want to take a derivative, then we can look at a derivative of the derivative. So what we'll do is we'll replace this y here with this quantity, dy dx, and then these two can be made to be the same, so that the second derivative is d by dx of dy, which is this quantity here. So d by dt gets swapped out for the y, dy dx, and the bottom remains the same. Okay, so it's a little bit of shuffling about, but it's a simple, straight substitution. It helps to look at an example on how to work that. Two things we're going to do in this example. We're going to, again, compute a first derivative. We're going to compute a second derivative and use that second derivative to say something about concavity. Nice. Looking at these parametric equations, this is a circle. This is parametrizing a circle. And the circle is centered at the origin with a radius of 3. Let's go ahead and tackle finding the slope. We use that dy dx is the quotient y prime over x prime. If we look at y prime, we want to take a derivative of sine, we get cosine. Down in the bottom, we want to take a derivative of cosine, we get negative sine. The 3's cancel out. Cosine over sine is cotangent, and it's prepended with a minus sign. To find the slope at this point, corresponding with t equaling pi over 4, we would simply plug in. We're also going to be considering the concavity, which means a second derivative. So let's go ahead and compute that. What we do is we set up our notation. We want a second derivative. And then by the formula, all that we're doing is replacing this y with this quantity. That would be a derivative of this function. So we do d by dt of that first derivative and then place it over x prime. X prime, we can see from our previous computation, is just negative 3 sine t. In the numerator, we do the computation. Cotangent under derivative goes to negative cosecant squared. And so we get cosecant squared, positive cosecant squared in the numerator. And then that just simplifies to negative 1/3 cosecant cubed t. Nice. So here we have the first derivative as a function, second derivative as a function of t, and then we just simply plug in the parameter t at this value. We get a slope of negative 1, and the concavity will be concave down since the second derivative is a negative quantity. And that's summarized here. Okay, so the key thing is this computation of the second derivative, that you're plugging in to the numerator a derivative of the first derivative. Denominator, you're reusing what you had. One for you to do, compute the second derivative for this parameterized curve. Next, determine all points at which the horizontal and vertical tangents exist. So you will find a horizontal tangent if that means that there is no rise if y prime is 0. There will be a vertical tangent to the curve if there is no run, and that means that x prime is 0. All right, second order done. Let's move on to an application here in section 7.2, arc length. We can go back and we can recall that the circumference of a circle of radius r is given by the formula 2 pi r. Let's go ahead and break that down. And let's introduce points along the circle. And then let's name the points. Let's start with the 0th point, the first point, the second point, and so forth until we come back to where we began. And then let's pick some arbitrary successive points, the I minus first point and the ith point. Let's expand our view. Let's open up the circle and then bring in these arbitrary points so that we can consider the distance between them. Now, this pink dot and this pink dot, I've named them pi minus 1 and pi, but they're points in the plane so that they would have an x-coordinate and a y-coordinate, where the x-coordinate is found by plugging into the parametric equations t sub I minus 1, and pi, the x and y coordinates, are found by plugging in to the parametric equations ti. Nice. What you want to note in this picture is that the arc length between the 2 points can be approximated by this hypotenuse. So let's give the name the hypotenuse di, and then focus on finding an equation for a formula to compute di. Well, it's pretty simple. You just use the Pythagorean theorem. In order to use the Pythagorean theorem, let's label the base and the height, the 2 legs, change in x, change in y. Apply the Pythagorean theorem. The hypotenuse will take the form as the square root of the sum of squares. Perform algebra. Multiply each summand by 1 in the form of delta t squared over delta t squared. Rearrange that so that you can pull off the delta t in the numerator. Apply the radical to the delta t squared to get delta t on the outside. And this is the form that we want to use to represent this hypotenuse between 2 points, pi minus 1 and pi. So that the more and more points we take, the closer and closer these points will come together. The smaller and smaller this di will become. So again, more and more points that we take is going to push the points closer and closer together so that the di better and better approximates the true arc length of the circle, which means that the true arc length can be found approximated by summing up all n of these di's. And this sets up a Riemann sum so that the true arc length can be recovered by taking a limit in the ends. And then we'll say that we begin at p naught, corresponding with t equaling a, and end at the very last point with t corresponding to b. And then this is the arc length formula. Radicand this radical function. Very good. So using that formula, confirm that the circumference of a circle of radius r is 2 pi r. And then assume, or use the hint that a circle of radius r is parameterized by x equals r cosine t, y equals r sine t. And then plug into the formula. Nice. That is a quick overview of arc length of parametric equations. Finishes section 7.2. Thank you so much for watching. See you on the next one.